My name is Ruben Feynman, and I'm going to be talking to you today about generating new concepts with neuro-symbolic models. And this is joint work with my PhD advisor, Brendan Lake. So consider the conceptual knowledge that enables a chef to produce new recipes. Now, a chef knows that recipes are built from reusable ingredients, or parts. Now, they also know that it's not just a free combination of parts. There are rich correlations between ingredients in a recipe. For example, some ingredients can substitute for others, such as butter for oil when greasing, and some ingredients should never be used together, such as ketchup and milk. And finally, the chef understands the causal processes used to compose a recipe from a set of ingredients. So this knowledge is compositional, is causal, but it also includes an understanding of statistical correlations. Now, in computational models of conceptual knowledge, previous efforts to integrate structure and statistics have demonstrated ways of performing statistical inference over structured representations. Now, in accounts of this kind, statistics is primary in selecting between structured symbolic hypotheses, but plays little role in forming the individual hypotheses themselves. And this limits the type of conceptual knowledge that we can model to that which can be expressed through rigid parametric distributions. So we're proposing a different approach to synthesizing structure and statistics through hybrid neuro-symbolic generative models. And the goal is to design a generative model that represents the compositional and causal processes behind observations, while simultaneously modeling non-parametric statistical relationships. And our proposal is to use probabilistic programs with neural network subroutines. The control flow of the probabilistic program is an explicit representation of the causal generative process that produces new concepts, and explicit reuse of parts through repeated calls to reusable neural network subroutines ensures a representation that's compositional. But the distribution of parts and correlation between parts are represented implicitly by neural nets, and this allows the model to capture non-parametric statistics. As a case study, we explored a generative neurosymbolic model of handwritten character concepts. And the generative process to sample a character from our model proceeds as follows. We begin with a blank image canvas. And at every time step, we sample the next stroke given the current state of the canvas with the procedure generate stroke. And generate stroke consists of two neural network modules, and I'll refer to my poster for the details. And after sampling a stroke, we render it to our image canvas using a fully symbolic renderer, and we sample a termination indicator telling us whether to stop or to continue with another stroke. We repeat this process until we reach a termination, after which we return the final image canvas. Now, we're going to train this model using the omniglot dataset, which is a readily available dataset of simple character concepts, and it includes real-time drawing data for each character. And our goal is to use the drawing data to model the causal generative processes that produces characters. We're going to train our model on many character classes and then evaluate log likelihoods on held-out character classes, i.e. novel character concepts. And we also ask our model to generate new character concepts, and we will evaluate the productions. So we tested our model for its ability to generalize to new characters from novel alphabets, looking at test losses or negative log likelihoods. And in a threefold cross-validation experiment with omniglot training set, we found that it outperformed a baseline LSTM model in all three folds. And we also compared performance on a completely withheld set of novel characters. And again, our neurosymbolic model outperforms the LSTM, and its outperformance was statistically significant. And in addition to our quantitative evaluations, we also looked at a new character sampled from our neurosymbolic model and compared them with alternative models. Now here on the top right, I'm showing some ground truth characters from the omniglot dataset. And in the center row, I'm showing some characters produced by our neurosymbolic model on the left box, an alternative LSTM model in the middle box, and also from the fully symbolic Bayesian program learning model, right box. And compared to the symbolic BPL model, both of our neural enhanced models appear to capture more correlation structure and character complexity. And if, for example, if you look at the second row, first column of the neurosymbolic box, The model propagates stylistic and structural consistency across 3 strokes from a Braille-like character. So in summary, the neuro-symbolic model captures more correlation structure compared to fully symbolic models like BPL, and it generalizes furthest from the training examples compared to other neural network models. And in addition to making sure that our model's character productions are structurally consistent with ground truth, we also wanted to make sure that they're novel, i.e. sufficiently dissimilar from training examples. So we conducted one additional evaluation where we looked at the nearest training neighbors for each character production, and I will refer to my poster for the details of this experiment. Thank you.